Hey everybody, it's Bruce and the dog on the floor, and today we're going to be staying a little bit longer in math land. That's right, we're talking about Julia's machine learning library, Flux, and we're going to be focusing on the elements of the math that relate to multi-dimensional input. So recall that machine learning is all about taking data that we're going to split across some observations and predictions that we can make with those observations. And then we're going to feed that data into a model, and then we'll train it up, making slight improvements in the model over time so that we can make better and better predictions. And then we'll compare those predictions to the data that we have on the upper left-hand side. So when we think about the model is just a function. And so this is essentially the structure that we're looking at. We've got some input, we're going to feed it into a model, and that's going to lead to some outputs. So you might be asking the question, what makes this a neural network? You might say that doesn't have a shape that's network-like at all, or like any individual neurons that have multiple inputs and outputs. And so we're going to talk in this video today about the abstraction that model represents. So the cool thing about Julia, and especially Flux, is that the model underneath that M is exactly the same as the math abstractions underneath that M. And so that means that the math for this machine learning network hides the layers beneath it, just like our software does in a well-defined system. So what we're going to do is we're going to peel back those layers one at a time so that you can see the things that make this multidimensional and actually turn this from a flat model to a network. All right, so the first thing is that this thing is built in layers. And you might ask what the layers are. Well, you've seen them. In fact, the FizzBuzz example had the dense layer. And in fact, it had multiple dense layers like this. And what's cool about that is that we can talk about the overall model, and we could actually use the model as if it was one long function, but under the covers, we can break that down into individual layers where it's really easy to reason about them and define how they work. And that's the essence of a neural network. And you might ask what each individual dense layer does. Well, each one implements a pretty basic function, wx plus b. And we've talked about it before, but when those individual W's and B's are individual values, this is basic. But what we're going to do instead is we're going to feed multi-dimensional inputs into them. And as we feed them across the layers of the neural net, we're going to see multi-dimensional outputs. And then we're going to choose from one of those to build an output that might be like the choice of a category, like fizz, buzz, or else. And so that's how our inputs are going to be processed. They're multidimensional. But to process those inputs, we're going to need multidimensional weights and inputs and biases. So if all these things are multidimensional, we're going to need to define how those individual operators work. So that means that we also need multi-dimensional operators. And today we're going to spend a good amount of time talking about two of these operators. The first one is the matrix multiplication. And this is how we're going to take a multi-dimensional input and feed it into a function and generate a multi-dimensional output. We're also going to talk a little bit about matrix addition. In Julia, that's implemented with a broadcast. So we'll talk about how that works as well. And when we're done, you're going to have a sense for how this simple m of x works as a function with a lot of complexity underneath it, so that when it makes sense, you can think in terms of a simple model. And when you need to break it down to access the individual layers of your implementation, you're going to be able to do so. So this is what that broadcast does. Now, what we're really trying to do is take the result of that w times x, which is going to be a matrix. We don't know what exact dimensions it's going to have yet. But then we're going to take that plus, and that is broadcast because of the dot modifier on its left-hand side. And we're going to add the b to everything in that list. So here's what that looks like with a one-dimensional list. So I might want to broadcast a +1 to everything in that list. And it does exactly what you think it does. It adds 1 to the first and second and third elements on that list. And I'll pause for a second to let you kind of take it in. Okay, but sometimes that broadcast operator might be a little bit more sophisticated. And so I might have a multi-dimensional input and output. So that might mean that I want my bias to be not just one element, but several elements so that I could add them to every chunk of a dimension. And here's what that looks like. So let's say I want to broadcast the dot plus, and I want to specify a whole column with 1 in row 1 and 2 in row 2. And I want to add that to every column on the left-hand side. So the first thing I'm going to do is I'm going to take that 1 and 4 and I'm going to add that to the 1 and the 2, and that's going to give me a 2 and a 6. And then 3 and 7, and then 4 and 8, just like that. So this is how broadcast works. And it's going to make it really convenient to add a bias to multi-dimensional output. And so the next step that I need is to process that W times X. And that's going to be done with matrix multiplication. And we'll get to that next. Sometimes people have trouble with matrix multiplication, at least getting the idea behind it. So what I'd like to do is bring up a particular example. So let's say that Anne is shopping for a couple of items, and the items that she wants are nuts, eggs, and figs, and they are listed row by row in the matrix on the left-hand side. So Anne is a column. We're going to multiply that whole column by a row, or everything in it, and then we're going to add the results together. So how much is would Anne spend with this shopping list and the prices, the shopping list on the left and the prices on the right? Well, Anne's going to get 1 bag of nuts for $9, 0 bags of eggs for $1, and 2 bags of figs for $3. And then that's going to lend a price of like $15 or something like that. So this is basically what's happening here. Now, we can also process this across multiple dimensions. So let's say that both Anne and Bob are shopping, and they're both looking for nuts, eggs, and figs. And so we already know how to process one particular dimension. This is one dot product. And so we could repeat the same process on the right-hand side. So if you look at this really carefully, you're starting to get a hint for the multi-dimensionality of the approach. So what is the matrix on the right-hand side? Well, if you think about it, it's particular weights, where the weights, you could think of the weights as the individual prices of these items, right? Each bag of nuts is going to cost you $9. The weight of 9 for every item that you get. And so this is exactly how the matrix multiplication is going to work in the WX plus B. So we don't have to stop with this 2 dimensions on the left and 1 dimension on the right. You can imagine that I might also be shopping at different stores. Now, I grew up in the South, and in Memphis we had Kroger, and in Texas we had H-E-B. But these grocery stores might have different prices. It might be that Kroger is just a little bit more expensive for most items and cheaper for figs. So this is what we would do in that case. We've already multiplied the first couple, so we know what that looks like. But we can also do the same type of matrix multiplication, multiplying a column on the left to a row on the right to get the individual values. And so this is how we actually build matrix multiplication, and this is how we choose the dimensions. So if you think about it, we have a couple of different observations, and then we have a couple of different features These are the dimensions. So we have this chunk of input data with features and observations, but what we really mean is rows and columns, and we should ask ourselves what that means for the model. We have this input and we're firing the input through a couple of functions, and these are just dense layers, and it's going to generate a certain number of outputs. What do I mean by inputs and outputs? Well, we've already determined that the input has a number of features that's represented by rows, and the outputs have a number of outputs that are also represented by rows. And the input features might be things like divisible by 3, divisible by 5, and divisible by 15. And the output features may be the categories for prediction, like fizz, buzz, or else, just like it is with our fizz buzz problem. Or maybe the inputs are the number of square feet for a house, and the number of bathrooms in a house, and the distance from local employers. And the number of outputs, well, there might only be one, the price of the house. Well, that's the number of rows. So 3 on the left, 4 on the right. Well, how many columns is this table going to have? Well, it might just have one if we want to feed it one input, or it might have more. In fact, the number of columns is variable. There might be 4, there might be 2. And it turns out that the number of inputs is actually the first argument in that constructor for the dense layer. And then the second argument is the number of outputs. Well, in this case, there's a hidden layer in the middle, and those question marks there have to match. So the number of outputs on the left has to match the number of inputs on the right. Well, how many outputs do we have? Well, it has to match the shape of the output matrix there. So there are 4 rows and 4 outputs. So they have to match, and in this case, we are good to go. So let's talk about what that question mark is. Well, it might be 6 different rows. How many columns is it going to have? Well, it's going to have the same number of columns as the observations on the left and on the right. That's going to be repeated all the way down the neural network. And you might ask yourself, well, what if we had 2 hidden layers? Then this would have 2 rows. And we could change this based on the shape of the data. Or what if I had 4 observations? Well, at each stage, this neural network is going to take as inputs and outputs matrices with 4 individual columns. Okay, so if that's how the dimensions are going to work for each individual matrix that feeds into the next layer or is output from the previous layer, let's think about the formula in the middle, and that's the Wx plus b. Each dense layer, that's all it ever does. And if you think about it, the dimensions of B are going to be the number of rows of W and the number of columns in X. Well, the number of columns in X is always fixed to the number of observations. So that one's easy. And what about the W? Well, the W is determined by the number of rows in those weights. And so that's actually also the same as the number of outputs for the neural network. And what about that number 3 that you see? Well, the number of columns in the weights has to match the number of rows in the input. So that has to be 3. So anytime that you see that Wx, the dimensions of the weights has to be the inverse. So if you have a dense layer with 3, 2, the weights are going to have the dimensions of 2, 3. So it's going to look a little bit like this. So the weights we're going to feed in a matrix that has 2 rows based on the number of output rows that we want to generate, and it's going to have 3 columns based on the number of input rows on the left-hand side, because that's X. And then we're just going to repeat this process all the way out. And then all you have to do is think about this in terms of the layers, right? So we have the number of features and then the number of observations. And the number of features is going to be the number of rows in the input. The number of observations is going to be the number of columns in the output. And then all you have to do is stitch these pieces across, right? So any interior dense layer, the number of outputs has to match the number of inputs on the other side. And then eventually, all the way on the right-hand side, the number of outputs that you expect will just be output to the result that you're trying to build. And so what happens? This still doesn't look very much like a network. But if you break down the individual math that's happening, all the additional formulas, it really starts to look like a network. So if we have this WX, this is going to be multiplied by each individual weight in the system. Each one of these weights is a different one. Each one of these X values is a different component of the individual input. And the weights are going to determine the strength of an individual connection. And obviously I'm oversimplifying this a little bit, right? Because this isn't everything that's happening within one little formula within our neural network. Let's drill down into one of these. So one of these is W3 times X3. And remember, this is going to be a dot product, right? But that's not the only thing that's going on. We also have this activation function. Remember, we can't make nonlinear predictions with something that looks just like a line. So we're going to feed this activation function, and normally we're going to name it with this sigmoid, but it's just a broadcast function. The second thing is we're going to tack on a bias, and the bias is also going to be multidimensional. And then in the middle, we have this matrix multiplication, right? So that's that dot product that we talked about, and it's going to have inputs from across the network. So in this case, the dot product is relatively straightforward, but this is going to get longer and longer as there are more and more observations. And so the impact is that this format we're going to start to express all those formulas with a dot, because even though they're relatively complex formulas, we have the activation times WX plus B. We essentially want to think of them as individual neurons with properties of the math that feeds the next layer in the network. So it's pretty cool. That means that really, when we're building the neural networks, all we have to do is think about the dimensions of the multiplication that's happening in any one layer. And so when we do that, we can start to imagine neural networks not as complex formulas, but as really simple ones that expand to a behavior that's a lot more exciting. And whether I have just one layer in the middle or multiple layers, just like our FizzBuzz model. And that's an excellent thing. For Bruce and the dog on the floor, this is Groxio Learning.